This is the Sun. The Sun is a main sequence star, one of many in fact. Main sequence stars make up 90% of all stars in the universe. While the Sun is fairly big relative to our solar system, making up 99.8% of all of its mass, it's actually an average-sized star, with only 3.5% of all known stars being larger than it. Main sequence stars, like all stars, originate from nebulas. Nebulas are giant clouds of gas that can sometimes span upwards of 100 light years across. They are primarily composed of hydrogen, helium, and other ionized gases. Even though nebulas are far denser than the vacuum of space around them, they are still far less dense than any vacuum we can create on Earth. Nebulas oftentimes originate from stars gone supernova. It is here that new protostars will be formed. After a significant amount of time has passed, particles begin to hit one another and clump together. This clump will start to generate its own heat, which will gradually become a protostar. This protostar is the beginning of a young star. These stars, while not making much light of their own, stick out among their surrounding nebula cloud in infrared. Several protostars can form in one nebula. The number can vary, though, on the size of the cloud. And after a significant amount of time, this protostar will enter its third stage of development called the Titari phase. But these stars are still less than 10 million years old, and can typically last for about 100 million more years in this phase. These stars are often found near molecular clouds and are on their way to becoming what has been dubbed a main sequence star. But if this star fails to achieve fusion, they become a brown dwarf. Brown dwarfs are just basically planet-like stars able to only fuse deuterium. A star is officially a main sequence star when it is able to fuse hydrogen into helium. Main sequence stars vary drastically in size, and this size greatly affects the length of the star's lifespan. These stars' sizes can range from just about 10% of our Sun's current mass to 200 times as massive. It is thought that our Sun will live for about 10 billion years, while a star weighing only 20 times more will only live 10 billion years. Once one of these stars has consumed all of its fuel, it enters the final stage of its life, a red giant. When a star can no longer fuse hydrogen into helium, gravity begins to squeeze the star smaller and tighter. This causes it to get far hotter and denser. This new increase in pressure has now caused helium to fuse into carbon at much faster rates, creating much more energy. This increase in energy causes the star to push back and swell in size. It's even thought that in the very distant future, our own Sun will reach this stage too. It's predicted it will grow to be about 200 times its current radius, which would end up swallowing Mercury, Venus, and maybe even the Earth. And just for an example, this is about what it would look like if the Sun was 200 times its current radius. And although red giants are massive, they are not the largest. That title belongs to the hypergiants. But due to the extreme rarity of these colossal stars, not much is really known about them. What we do know is that they have an extremely high luminosity, mass, size, and mass loss because of their extreme stellar winds. These stars only occur among the most giant of main sequence stars. Hypergiants are so massive, they quite literally tear themselves apart. At the surface of the star, gravity is so weak that it can't hold on to its own mass, and tons of material gets ejected off into space. Powerful stellar winds end up taking the majority of the mass at the surface of the star. Even though the Sun is small compared to these hypergiants, it still loses about 4 million tons of mass per second due to fusion. But a star like Betelgeuse blows away an amount of matter equal to 2 Earths in just 3 years. There are 3 main varieties of hypergiants. On the far left is the blue hypergiant, known as the Pistol Star. This star has a radius 300 times greater than that of the Sun, and 25 solar masses. To the right is Rho Cassiopeia, a yellow hypergiant. Although this star is just over 8,000 light-years away from Earth, it can still be seen with the naked eye. It weighs about 40 solar masses and is about 500 times the radius of the Sun. It is about 500,000 times brighter than that of the Sun. And if Earth were as close to Rho Cassiopeia as it is to the Sun, we would be inside it. But not much else can be said about yellow hypergiants, as only 15 of them are known. The last two are red hypergiants, the one after Rho Cassiopeia being Betelgeuse. Betelgeuse has a mass of approximately 11.5 solar masses, and its radius is 887 times that of the Sun. It is 642 light-years away from the Earth, yet it is the 10th brightest object in the night sky. The next star is VY Canis Majoris. Despite being near 5,000 light-years away, it is still a very bright star in the southern constellation of Canis Major. It has a mass 17 times bigger than the Sun, and a radius 1,420 times that of the Sun. To get a better scale of things, I'll be using this picture. The same order of stars still apply. If you look to the left of the Pistol star, there are two circles. In the gray circle, which represents the orbit of the Earth, is one single pixel representing the Sun. The red circle represents the orbit of Jupiter, and the half-blue circle represents Neptune's orbit. But now it's time I show the largest of known hypergiants, Stephenson 218. I'll be using the Sun as a starting point and various other large stars for reference. That was Stephenson 218. But how big is it exactly? Well, to put it into numbers, it is roughly 2,150 times the size of the Sun, and nearly 500,000 times brighter. Even if you were to travel at the speed of light, it would still take you about 8.7 hours to travel around its circumference once. Our fastest plane on Earth, traveling at a constant speed, would take around 500 years. Relative to other stars, the lifespan of this star will be extremely short, and will likely end in a massive supernova, once again starting the cycle for new stars to be born in the remnants of its death. When more massive stars have consumed most of their hydrogen and have started fusing silicon into iron, they have reached the final moments of their life. Soon, these stars begin to implode in a supernova. The result of this implosion is usually a neutron star, but if the star is big enough, it can become a black hole. Neutron stars themselves can be very hard to detect, as they emit very little radiation. But when a neutron star is born, they oftentimes start out as pulsars. A pulsar is just a star, usually a neutron, sometimes a white dwarf, that is spinning very rapidly. This rapid spinning causes beams of radiation to be emitted. While to us it appears that it is pulsing, the pulsing is actually due to a misalignment of the neutron star's rotational axis and its magnetic axis. This is somewhat comparable to the beam of a lighthouse. Only when it is facing us do we see the beam. These stars produce an insane electric field, with an electric potential of upwards of 1 trillion volts. A single cubic meter of the magnetic field in the Crab pulsar contains more energy than humans have ever been able to generate to date. It is with neutron stars that things get even crazier. Imagine a star with 1,000,000 times the mass of Earth, all compressed down into a city about 25 kilometers wide. And these things get hot. The surface of a typical neutron star is 1,000,000 degrees Celsius, meanwhile our sun is only 6,000. Similar to Earth, neutron stars have an atmosphere, crust, and core. The crust of a neutron star is extremely hard. The top layer of the crust is made of leftover iron from the supernova squeezed together in a crystal lattice, with electrons freely flowing through them. As you go deeper in, gravity is even more extreme. Iron nuclei end up being pushed into one another. At this point, very few protons are found as most merge to neutrons. At the base of the crust, the iron nuclei seem to make long strands and then sheets. This is literally called nuclear pasta. It is thought that this nuclear pasta is literally the strongest material in the universe. Scientists aren't quite sure what the core is like. Some think that protons and neutrons simply can't exist at this pressure and simply dissolve into quarks. Some have even theorized that these quarks turn into strange matter. But strange matter is entirely theoretical. All that is really known about it is that it would have extreme properties, unlike anything else we know. Or protons and neutrons might just stay the same. We don't really know. Things are far too extreme inside the core of a neutron star to know. Something really cool we do know is that when two neutron stars collide, they explode in what's called a kilonova. It's thought that gold, uranium, and platinum and all other heavy elements originate from such violent explosions like kilonovas. And oftentimes kilonovas end up producing black holes. Black holes are the most extreme thing in the universe. No particles or even electromagnetic radiation such as light can escape from it. They have an insanely strong gravitational pull, so strong in fact that it is believed in the center of most galaxies lies a supermassive black hole. While they themselves cannot be seen, their interaction with space around them can. Matter that falls onto a black hole can form an external accretion disk that is heated by friction. This forms what is known as quasars. Quasars are some of the brightest objects in the universe. These things have an energy output of up to 1,000 times more than the entire Milky Way galaxy. But now back to black holes. All matter that enters a black hole is believed to be crushed into an infinitely dense point. This point is called the singularity. But that's kind of all the information I got. Thanks for watching. See ya. Oh, and if you're curious how this video was made, it was made using a game called Universe Sandbox.